Good afternoon. Thanks for joining us virtually. My name is Qingchuan Zhao, a PhD student from Ohio State University. Today, I'm going to talk about how to automatically uncover hidden behaviors from input validation in mobile apps. This is a joint work between OSU, NYU, and CISPA. Today, mobile apps are everywhere, and they have provided many useful functionalities to billions of users around the world. For example, we've been using mobile apps to check weather, communicate with friends, shop online, and so on and so forth. Unfortunately, some apps can also contain hidden behaviors that are not publicly disclosed to users. These behaviors could be just Easter eggs that are designed to surprise users, such as when a user taps happy birthday in some chatting apps, it will show the corresponding emoji icons. In addition, there also could be blacklists that disallow mentioning of certain sensitive words. Even worse, there could also be some other hidden behaviors that can give advantage to attackers, such as a master password that can be used to unlock secret files hidden by a user. Let me show you several motivating examples of these hidden behaviors from real-world apps. The first example is from a news app that validates its user's nickname against a blacklist of keywords. This app has more than 50,000 installs from Google Play and 1.1 billion installs from all alternative markets together. To do so, the app first reads a user's nickname at line 3, and then it goes into a validation method where it compares the nickname against a list of words, checking whether it matches any of them. And this list is loaded from a local file which contains offensive content. If there's a match, then the app will say, nickname contains illegal characters, and this nickname is not allowed to use. The second example is from a security app, Lost Android, which has 10 million installs, and the developers have fixed this vulnerability right after our disclosure, so we feel comfortable to share the details here. Basically, this app is designed to protect users' data when their phones are lost. From its code, we can see that it reads the user input at line 3 and compares this user input twice at line 5. One is to compare with a value read from database, and the other one is a fixed value. Both comparisons are checking equivalence, and these two conditions are linked with the OR logic relation. If either of them is satisfied, then the app will allow you to log in to access those protected data. Therefore, this string is a master password that can override the correct one set by a user. The last example is from a popular translation app that has 1 million installs. This app contains an access key to remove advertisements for free. Still, it reads the user input at line 6 and compares it with the string value at the same line. Here, the string value has been redacted because this one has not been fixed. If there's a match, then the app will hide advertisement without the original required payment. In order to uncover these hidden behaviors, we designed and implemented a static analysis tool, input scope. At a high level, it takes an APK file as input and detects whether such an app contains suspicious user input validation. Next, it resolves the value of comparison content, as well as understanding where it comes from. Then, it moves on to uncover the code dispatches of the comparison and construct the comparison context to identify different types of hidden behaviors with a set of policies. Let me show you the details. First, the objective of this component is to detect and pinpoint secret exposing validations. To do so, we use static taint analysis to taint user input and monitor its propagations. So the 10 sources are system APIs that read user input, and the sinks are APIs for checking equivalence. Here, we cover both the direct checking method, such as equals, and indirect checking method. For example, we can use map.get to know whether an object is in a map that performs exact value matching. After tracking the user input to the validation location, next, we need to focus on the comparison content that sits at the other side of the equivalence formula. In particular, we need to know where it comes from, how it is generated, and what is the value. Therefore, we first apply backward slicing to track the comparison content backwardly to where it comes from. And in the meanwhile, we can collect information about how it is generated. Basically, it can come from internal sources, such as programming code, local files, databases, and shared preferences. It can also be external sources, for example, user input and data from servers. After understanding how a string is generated, then we use string value analysis to simulate string operations, such as substring and append, to calculate its final value. Next, in order to uncover and identify these secrets, we need to build a comparison context that is constructed from the sources of comparison content and the code dispatch behaviors. Now we are missing the code dispatches. Here, we use a pair of two attributes to present a code dispatch. One is how many times a user input is validated within a judgment block, and the other one is how many potential branches could be taken if the validation is satisfied. In total, we have 3 dispatches. First, 1 to 2 dispatch. For example, in an if and else block, a user input is only compared once, and regardless of whether the condition is satisfied, there will be 1 branch to take. So totally, there are 2 branches. Therefore, it is 1 to 2. Second, many to 2 dispatch. For example, in a loop, a user input is compared with every element of a list. Therefore, there are many conditions. Regardless of which condition is satisfied, there will be 1 desired branch to take. So it is many to 2. Finally, many to many. For example, in a switch case block, a user input is compared with every case. So there are many conditions. And each case will lead to a different branch. There are many branches. That's why it is many to many. Finally, combining this code dispatch with the sources of comparison content, we can build the comparison context, where we can apply a set of policies to identify different types of secrets. In total, we define 4 policies. First, access key. It has 1 to 2 dispatch, and the comparison content is a hard-coded string. Just like this example. This fixed value, which is not supposed to be known to users, can serve as a key to unlock a behavior, so we say it as an access key. In addition, the access keys have many functionalities. I'll show you later. Second, the policy to identify a masked password is that it has many to 2 dispatch. Comparison values are from different sources. One of them is a hard-coded string. The point is that a fixed value can override the values from other sources to perform the same action, just like this example. So we call it a masked password. Third, blacklist. It has many to 2 dispatch. The comparison values are all from the same sources. In this scenario, all the comparison content together can form a list data structure, and the user input is compared with every element to check equivalence, just like this example as a blacklist. The last policy is to identify secret commands, and it has many-to-many dispatch, and at least one hard-coded value. In this case, it means that a user input can take a value from a set of strings, and each string can trigger a different action. Like this example, if user input is 1, then do function 1, if 2, then function 2. It is very similar to a terminal that accepts different commands and acts accordingly. So we call them secret commands. We have evaluated our tool on a set of total 150,000 apps, where 100,000 are from Google Play, 30,000 pre-installed apps from Samsung's firmware images, and 20,000 apps from an alternative market, Baidu market in China. In total, we have found that around 7,500 apps contain access keys, 500 contains master password, and 6,000 contain secret commands. In addition, around 4,000 apps contain blacklist. Let me show you some more interesting details about our result. First, the access keys. We have manually inspected a set of top apps with more than 1 million installs from Google Play, and there are 3 common usages. First, we can use that to log into the app's admin interface. For example, in this app, I didn't show their full package names and the actual keys because they have not been fixed. Its interface for admin login is hidden in the corner and is invisible to normal users if not searching for that on purpose. Second, it can also be used to reset a user's password. For example, there is a secret key that you can use in a screen locking app. If you failed to provide the correct password to unlock the screen several times, it will show a hidden button that leads to an interface where accept the code to reset the password. Another common usage is the bypass advanced service payment. As shown before, we've seen some apps will accept the code to remove their advertisement displayed in the app without payment. Next, master password. Here we show the top 10 apps that we have manually checked with our best understanding. To our surprise, we found even apps providing security-related services have this problem. One is a Lost Android. The other one is a file encryption app that allows users to hide or lock files with a password. But with this master password, we can view and unlock all hidden files for all users. Another interesting case is that there's one app that when we use a master password to log in into another user's account that we create ourselves for testing, the app allows us to log in, of course, and in the meanwhile, it also shows a text at the bottom saying wrong password. Next, secret commands. Basically, these commands can be classified into 2 categories. First, debugging. For example, turning the app into debugging mode. Second, app-specific functionality, such as clear user settings or upgrade to a pro version. Finally, blacklist. We manually investigated 20 top apps, 10 from Google Play, 10 from alternative market, to understand the details of the blacklist. Because of the extremely inappropriate content, here we only show their classifications, including insulting words, illegal drugs, and others. More details can be found in the paper. Discussion. First, why such hidden behaviors exist? The first possible reason is that developers still misplace the trust. We'd like to suggest validating security-relevant user input on backend servers, or consider using trusted hardware components such as trust zone. Another possible reason is that developers may carelessly forget to remove debugging code before releasing, because many secret commands are supposed to do debugging things. Limitations. Currently, we are not supporting analyzing user input validation in web view component because we focus on Java bytecode level. We only focus system APIs for string comparisons. and may miss related string operations that are customized by developers. Also, we are not covering cases that use database queries to validate user input. And there would be also false positives. Currently, we can now distinguish benign Eastern egg cases, just like emoji icons. Our related work includes static tint analysis, input validation, user input analysis, and malware detection. For the sake of time, I'm not going to talk about them here in detail. Please refer to our paper. To conclude, I present Input Scope, a static analysis tool to automatically uncover hidden behaviors from user input validation in mobile apps. And our evaluation with 150,000 mobile apps discovered over 10,000 applications containing secrets, including blacklist secrets, access keys, master passwords, and secrets commands. And source code is available at GitHub. Thank you for your attention. Now, I'd like to answer any questions you might have.